New section. We have an equation that relates these quantities: the amount of heat, the mass of the substance, the specific heat capacity of the substance, and the temperature change. So Q equals mc delta T. So it's all spread out there. It's a little hard to see. Let's see if I can write it up here. Q, try that again. Q equals mc delta T. That delta looks a little bit like an A, and so some students remember this by saying Q equals mcat. So Q is the amount of energy, the amount of heat in joules. M is the mass of the substance in grams. C is the specific heat capacity that we just talked about. And delta T is the temperature change. Delta, this triangle, is a capital Greek letter, delta. And in science, we use that to mean change in. So delta T is the change in the temperature. And we always define that in the same way. It's the final minus the initial. So sometimes the temperature change is positive, the temperature went up. Sometimes the temperature change is negative, the temperature goes down. It's okay to have a negative temperature change. So here's a problem with a whole bunch of words in it. You find a copper penny in the snow and pick it up. How much heat is absorbed by the penny as it warms from the temperature of the snow, which is minus 5 degrees Celsius, to the temperature of your body, which is 37 degrees Celsius? Assume the penny is pure copper and has a mass of 3.10 grams. And it says you can find the heat capacity of copper in table 3.4. Well, table 3.4 is right over there. So here's copper. This is the specific heat capacity. This table gives units of joules per gram degree Celsius. If you look it up somewhere else, it might give you calories per gram degree Celsius. You need to pay attention to the units. So 0.385. So with a problem like this, it's really helpful to pull the numbers out and write down what they are. So we looked up the specific heat capacity for copper. And that was joules over grams times degrees Celsius. And then here's another number, 3.10 grams. And we have a couple of temperatures there. We have minus 5.0 degrees Celsius, and we have 37.0 degrees Celsius. So pull the numbers out, write down their units. It may not be immediately obvious to you what those numbers refer to. So you look at the question and it's like, okay, there's temperatures and masses and how much heat, and hopefully we'll figure out that the equation we need is Q equals mc delta T. And that will help us to identify what these things are. Here's C. We already got that because it basically told us to go look that up. So that's C. Which of those numbers is M? The 3.10, right? It says mass of, and the unit also tells us, because we should know that gram is a unit of mass. It's not a unit of temperature or volume, it's a unit of mass. And then we need delta T, but we've got two temperatures here. One is the initial temperature, one is the final temperature. Can you tell from the little story in the problem which one comes first? The penny was in the snow initially, at the beginning, and so its initial temperature is minus 5. You pick it up, and your body transfers heat to it and warms it up, and the final temperature will be your body temperature, 37. So that still doesn't give us delta T, though, does it? We need to remember that delta T is T final minus T initial. So delta T equals the final temperature, 37, minus the initial temperature. Be careful with that negative sign there. So we're going to get 42.0 degrees Celsius is the change in temperature. Started out 5 degrees below zero and went to 37 above. It's asking how much heat. Heat is Q. Don't ask me why they chose Q. I have no good explanation for that. But that's what it is. Q is heat. So we've got all of the pieces here. We've got M, we've got C, we've got delta T. Now we can just put them all together. So Q equals M, 3.10. Write the units in here. There's M. We'll put C, 385 joules over grams degrees Celsius. And then our temperature change that we just figured out, 42.0 degrees Celsius. Now look what happens with the units. The grams cancel and the degrees Celsius cancel. And the unit that's left is joules, which is a unit of energy. And heat is energy. So we'll take the calculator, 3.10 times 0.385 times 42 equals, and I don't really have a good place to write that. I'm going to write it up here in the middle. My calculator says 50.127. And the unit would be joules. And then we have to think about significant figures. How many significant figures does this number have? 3. And this one? 3. And that one? 3. So they all have 3. So our answer should have 3. So we're going to report our answer as 50.1 joules. That's the amount of heat energy needed to warm up that penny. Any questions? Yes?
Can this also be calculated by moles?
It could be calculated by moles if the specific heat capacity was given in moles, but it is generally not. Any other questions? Yes?
So for the pre-lab, did we have to do the significant figures and scientific notation?
For the pre-lab, you need to use significant figures and scientific notation. You should always give sig figs your best shot, okay? And I know that significant figures are tricky for a lot of beginning chemistry students. On the exam, there will be questions specifically about significant figures. Aside from those, I just want you to give it your best shot. I don't want to see you writing down all 9 digits from your calculator, but I don't want to see you rounding off too much either. Most of homework problems or anything like that is going to end up with like 3 or 4 significant figures. So in a pinch, if you're just completely mystified by the sig figs, do 3 or 4 and you'll be close enough. Scientific notation, it's never wrong to write the answer in scientific notation, but you only have to put it that way if it specifically says, and I don't think it says that on the pre-lab. So if you just write it in normal notation. My kind of rule of thumb is if you can look at the number and you don't have to get your finger out and count zeros, then decimal notation is fine. If you've got a number, if this was something like that with all those zeros, normally in science we don't use commas to separate like that. It's not immediately obvious how many zeros. That number should be in scientific notation. If you have a really small number, it's hard to count those zeros. It's easy to miscount them. Better to put that in scientific notation. But a number like this is just fine in decimal notation. Any other questions? Let's look at this equation a little bit more to maybe understand what it's doing a little bit. Let's pretend you are a football mom and you have to prepare dinner with a couple friends for the entire football team. And so you're making spaghetti, right? Because it's cheap and they're going to eat a lot. At home, if you boil water in a small pot, how long does it take to boil that water? 10 minutes or so? But the football team, you're feeding like 35 people, and they're really hungry, so you're using this ginormous pot. How long is it going to take to boil that water? On the industrial stove in the school cafeteria, 45 minutes to get the water to boil. How do I know that? Been there, done that. Does that make sense, though? A larger amount of water takes longer to heat. Why? It needs more energy to increase its temperature the same amount, right? The amount of heat needed, and that the stove is going to pump out the same amount of heat, regardless of how many gallons of water you have on top. The stove can only put out so much heat. So we see that it takes longer for more water because the mass of the water is greater. So if you have more water, if you have a larger piece of substance that you're trying to heat up, it makes sense that it's going to take more energy, right? So let's think about the temperature change. Put 2 pots of water on the stove. Same size, same amount of water. Put cold water from the tap in one, and put the hottest water you can get from the tap in the other. Which pot's going to boil first? The one with the hot water, right? Because the temperature change is smaller. It started out at maybe 120 degrees Fahrenheit and needs to get up to 212 Fahrenheit. The other one started out at maybe 60 degrees Fahrenheit, and it has a larger temperature change. So if the temperature change is bigger, it requires more heat. Does that make sense? You can think of it the other way as well. We talked about endothermic and exothermic, right? Exothermic means that energy is going out of the system. So if you spill a drop of boiling water on your skin, the water is hot, the energy goes from the hot thing to the cooler thing, which is your skin. And you feel that energy come into your skin. Does it hurt if 1 drop of boiling water falls on your hand? Yeah, but it's just kind of an annoyance, right? You're like, ooh, ow. What if a whole cup of boiling water spills on your hand? Does that hurt more? Yeah, a lot more. Why does that hurt more? The temperature is the same. The amount of water is larger. And so it has more energy that it can transfer to your skin. And that's why you're going to get a bad burn if you've got a whole cup of boiling water spilled on you instead of just 1 drop. So I'd like you to, at least on some level, understand what this equation is. And from your everyday experiences with heating water to make spaghetti, you have observed this phenomenon in action. Okay, so this does relate to everyday life. Okay, here's another example. A lead fishing weight with a mass of 75 grams absorbs 146 calories of heat. If its initial temperature is 47 degrees Celsius, what is its final temperature? I would imagine that many students look at a question like that and say, why would I even care, right? Who cares about heating up a lead fishing weight? Well, we're going to try to care because it's problems we need to learn how to do. So since we're talking about this Q equals mc delta T equation, we're probably going to need that, right? And there's a piece of information that's missing here. This fishing weight is made out of lead. We're going to need the specific heat capacity of lead. And so before I start writing things down here, I'm going to go back and look it up. In this table, for lead, the specific heat capacity is 0.128. So for this fishing weight, C equals 0.128 joules per gram degrees Celsius. We read the question, maybe it made sense, maybe it didn't. Let's pull the numbers that were given out of it and write them down. So we've got 75 grams, and we've got 146 calories, and we've got 47 degrees Celsius. And we know that Q equals MC delta T. Now let's identify what these numbers are. 75 grams, what is that? That's the mass. So we're calling that M. 146 calories, what's that? Calorie is a unit of what? Length, mass, energy. So that's a unit of energy. Heat is energy and Q is heat. It says it absorbs this many calories of heat. So that is Q. And this 47 degrees Celsius is obviously a temperature. Is that the initial or final? That's the initial. So this is Ti. And what are we trying to find? We're trying to find the final temperature. So I'm going to write TF equals question mark. That's what we're trying to find. So we look at that equation and we say, there's delta T in there, but there's not specifically T final. So there's a couple of different approaches to solving this. If we knew what delta T was, could we find the final temperature? Yeah. So how about if we take this equation and calculate what delta T is, and then figure out what the final temperature is? Algebra-wise, that's going to be simpler. So we'll take this equation, and we want to get delta T by itself. So we're going to divide by the things that are multiplied. We want the M's to go away. We want the C's to go away. It's like a teeter-totter that's balanced. If you divide by MC on one side, you have to divide by MC on the other side to keep it equal. So we're going to divide by MC. Now that's all messy, so let's write it out. Delta T equals Q over MC. So let's put our numbers in here. Q is 146 calories. You've got to write the units. The mass is 75 grams. And C is 0.128 joules per gram degrees Celsius. And then check out the units. Grams cancel grams. Do calories cancel joules? No, they're not the same, are they? That's like inches and feet. They measure the same quantity, but it's not the same unit. So what do we need to do? We need to convert one to the other. This one's all embedded and messy with these other units. What we need to do is we need to convert Q from calories to joules. So what I'm going to do is I'm going to erase it up here. We're going to fix the units and then bring it back. So over here we've got calories, and we want to make this into joules. So we want to multiply by joules and divide by calories. We're using dimensional analysis over here to convert the units. 1 calorie is equal to 4.184 joules. That's a relationship that you would look up if you don't remember. Calories cancel out. 146 times 4.184. So this is 610.864 joules. This is not my final answer. I'm going to consider how many significant figures the number has, but then I'm not going to round it off. I'm just going to use the whole thing in my calculation. How many significant figures should this number have? This one had how many? 3, and this one had 4. So this one should have 3. So I'm just going to underline that third one to let myself know this has 3 sig figs. And then we're going to take that number and put it up here. 610.864 joules. Now the joules cancel out. The unit that's left is kind of messy because it's a fraction and a fraction, right? We've got 1 over degrees Celsius. That ends up equaling degrees Celsius. If you want to see why that is, I could show you after class. Or you could just believe me. Okay, so now I've got the 610.864. I'm going to divide by 75, and I'm going to divide by 0.128. And I'm going to come up with a temperature change of 63.6317 degrees Celsius. If you come up with a temperature change of 1, then you're talking to your calculator wrong. I'll go over this sort of a calculation in a minute. There's just not room on this slide to do it. Mm-hmm.
For the bottom,
Mm-hmm.
75 grams,
Mm-hmm.
you multiply by 0.128.
Mm-hmm. The thing is, you're dividing by this quantity. And so if you see this as just multiplying, then you need to put parentheses around this. And do the 610 divided by parentheses 75 times 0.128, close parentheses equals. And then you'll get the right number. I'll go into more detail about that in just a minute. So we have the final temperature, we have the change in temperature. Delta T equals T final minus T initial. So what does the final temperature equal? The change in temperature plus the initial temperature. I need to get rid of this copyright thing down here so I can write on top of it. Oops. So if I add Ti to both sides, minus Ti plus Ti equals 0, right? And so what I end up with over there, that goes away. The final temperature equals the initial temperature plus the change. So the initial temperature was 47 plus the change of 63.6317. 47 plus 63.6317. The final temperature is 83.6317. What about significant figures? I forgot about them for a bit. This result here, we need to figure out how many sig figs this has. This one had 3, this one has 2, this one has 3. So this result has 2 sig figs. It's to the nearest ones place. So when we add 47 and 63,
You get a lot more than 83.
what did I do? I'm sorry. I don't know what I did. Oops. Let me fix that. 47. I did not ask myself, does this answer make sense? Yeah, 110. Does that sound better? Yeah. 110.6317. Here we have adding. This has uncertainty in the ones place. This has uncertainty in the ones place. So we're going to round this off to the ones place. And we're going to say the final temperature is 111 degrees Celsius squeezed into the corner. Any questions? Let's talk about this whole dividing by two numbers that are multiplied. Let's say that A equals B over C times D. This is the same as B over C times 1 over D. Would you agree with me? Now this looks like more the shape of the equations we did when we were doing dimensional analysis, right? And so if you're putting this into your calculator, you would go B divided by C times 1 divided by D. You wouldn't multiply by D, would you? On your calculator, if you do B divided by C times D, which is what this looks like, I will grant you that. That's what it looks like. What you end up with is this, B over C times D. That's not the same thing, is it? You've multiplied by D instead of dividing by D, and so you're off by a factor of D squared. So just be aware of that. There's 2 ways to do it on your calculator. So this is the wrong way. The way I do it is B divided by C divided by D. Everything that's in the denominator is divide by, divide by, divide by, divide by. I think that's the best way. The other way is B divided by parentheses C times D. Both of those methods will get you the correct answer, and then equals, of course. But this error comes up multiple times during the semester, and so I want to spare you from it, okay? So just be aware of that. Any questions? Okay, let's do another of these heat capacity problems. 328 gram sample of water absorbs 5.78 times 10 to the third joules of heat. Calculate the change in temperature for the water. If the water is initially at 25 degrees Celsius, what is its final temperature? So this question is similar to the last question. It's giving us some information and asking ultimately for a final temperature. What's something we need to look up that's not given in the problem? Water, the specific heat capacity of water. So if we go back to the table, 4.184 joules per gram degree Celsius. C equals 4.184 joules per gram degree Celsius. It says it absorbs 5.78 times 10 to the third joules of heat. So what letter does that have with it? Q, M, C, or delta T? That's the Q. So Q equals 5.78 times 10 to the third joules. And the other number we have here is 25 degrees Celsius. And what kind of a temperature is that? Initial. So that's T initial. This is actually asking us to do two separate things. What's the first thing it says? Calculate the change in temperature. So that's a delta T, right? So we have our equation, Q equals MC delta T. The first thing we need to do is find delta T. So we rearrange the equation first, and then we stick the numbers in. So we're dividing by MC to get rid of those. And then I have to do the same thing to the other side. So the change in temperature is equal to Q divided by the mass times the specific heat. So Q, 5.78 times 10 to the third joules, divided by the mass. Oh, I didn't ever write that down. That was right at the beginning and I skipped it. I'm sorry. 528 grams, that's M. So, did I say 528? Usually I say the right thing and write the wrong thing. I mixed it up that time just for fun. 328 times C, 4.184 joules per gram degree Celsius. These units should be written as vertical fractions. When you're writing by hand, it's just as easy to write it vertically as it is horizontally. When you're typing something into a computer, it's a pain to make it vertical. You have to get into an equation editor, and so it's much easier to just do a slash. But when you do a slash, it's easy to overlook the fact that you have a numerator and a denominator. So always write your fractions vertically. Check the units before you start calculating. Grams cancel grams, joules cancel joules. We're left with 1 over C, which is going to give us the temperature. So now we've talked about the pitfalls of a calculation like this. Let's see if we can do it correctly. You should also be very careful that you are using your scientific notation button on your calculator. So this number up here, use the EE or the EXP button on your calculator. If you have not figured that out yet, today is the day to figure it out. Because what that does is it tells your calculator that this is one number, not two numbers multiplied. Sometimes it makes a difference and sometimes it doesn't. But you don't want to get answers wrong just because you didn't talk to your calculator. So to enter this, it's 5.78 EE, or EXP, whatever your calculator has, 3. It's shorter that way. The EE button does times 10 to the for you. So I've got 5.78 EE3 divided by 328 divided by 4.184. So the temperature change is 4.2117 blah blah blah. And the sign and the unit is degrees Celsius. Is your calculator giving you that answer? If it isn't, check how you're entering the numbers. How many significant figures does that number have? Should it have? It should have 3. This guy has 3, this guy has 3, this guy has 4. So we're multiplying and dividing. We're going to choose the smaller, which is 3. So this is 4.21. So if we're recording that as our final answer, we would report 4.21 degrees Celsius as the change in temperature. And that is one of the things that it asks us for. But the other thing it asks for is the final temperature. So the final temperature equals the initial temperature plus the change. And that should make sense. You start at one temperature, you change it, and it might be going up because it's a positive change, or it might be going down because it's a negative change. And then what you get is the final temperature. So it's the initial temperature plus the change. Oh, there's just not enough room on these slides. 25.0 plus 4.2117. I'm gonna come up here. So we're calculating that the final temperature is 29.2117. And then we have to look back down here. The 4.2117 had uncertainty in the second decimal place, and the 25 had uncertainty in the first decimal place. So we're going to round this to the first decimal place, and this answer is 29.2 degrees Celsius. Any questions? These problems are challenging for a lot of students. And so if it's not crystal clear to you, what I would encourage you to do is when you get home, go to the YouTube channel and watch through this again. And when you get to the point where just the slide is up there, try to do the problem yourself without looking at your notes, without looking ahead in the video. And then if you're stuck, play the video forward a little bit. And do these problems over and over again until you can do them without any help. And then go do the homework to reinforce that. And that's the end of Chapter 3. So chapter and review, these slides just give you kind of a summary. I'm not going to read them, but I'm going to page through them slowly so the YouTube people can see them. So these are the big ideas from Chapter 3. These are the chemical skills, things that you should be able to do. You should be able to convert between temperature scales. You should be able to identify physical and chemical changes, etc.